In the first half of my lesson, we have considered the processes of hydrogeological risk, and in particular, the processes related to landslides and to groundwater flow. Now, in this second half of my lessons, we will concentrate on the hydrogeological impacts that could derive from climate and also global change. And at the end, we will make some considerations about mitigation and adaptation to these impacts. So let's start with the lesson. I'm sorry. Okay. So we considered before the aspects related to impacts by climate change. Impacts by climate change with a perspective both by the landslide process and the groundwater process. Impacts by climate change are not so easily predictable. And so it is very uncertain to have a clear evaluation of the effects of climate change. There is a high uncertainty to estimate which impacts could be expected in the future due to climate change in relationship to hydrogeological risk, so in relationship to landslides and groundwater flow. You know that there are different models trying to estimate, to assess the future climate in the Earth, and these models are called general circulation model. And these models are based upon emissions scenarios. So the scenarios of emissions of greenhouse gases in the atmosphere. And you know that these scenarios are very uncertain because it's very difficult to predict which will be the emissions and the global CO2 and other greenhouse gases concentration in the atmosphere expected, for example, in 2040, 2050, so at the end of this century, at the middle of this century. But there is a major consensus about two particular aspects: increasing of precipitation and temperature extremes, and obviously global warming. Global warming is a matter of fact nowadays. The increase of average atmospheric temperature, but we expect also an increase of the extremes of precipitation and temperature. So basically, we expect that also if the total amount of rainfall remain more or less in the same level or with some slight modifications, the distribution of the precipitation will radically be changed, with the total amount of precipitation concentrated in intense events. And between these events, we expect also an increase of the frequency of drought events. So events with lacking of precipitation and increase of temperature. So you see in the point number 3, we expect longer droughts interspersed with more frequent intense rainfall events. These can induce also modification of man's activity, and in particular, changes are expected in irrigation demand due to the increase of the production needs of crops, of agricultural crops, and to the increase of these dry events. And so we expect a strong increase of irrigation demand in the next decades. In this drawing, you see the summary of the main impacts of climate change on groundwater. We have impacts of different types, and all these impacts are in some way related to global warming and modification of the distribution of precipitation. So increase of intense meteoric events. One is related to the ice and snow at high altitudes, not only the melting of glaciers in the big inlands in Antarctica or in Greenland, but also the melting of glaciers in the mountains, like in the Alps and Apennines, for example, and also very important for groundwater recharge, the lowering of the height of snowfall and the lowering of the permanence to the ground of snow cover. So snow is going to be impacted in terms of total depth and permanence to the ground. This has an effect on recharge and on the capacity of recharge of the aquifer. Another important aspect, surface water, groundwater interactions. Groundwater is in equilibrium with surface water, and if surface waters, so rivers and streams, have a strong variability of runoff due to the increase of intense meteoric events and droughts, this variability reflects on the groundwater exchange. And so there is the chance that there is less recharge by surface water towards groundwater respect to before. Very strong modification in groundwater in relationship to irrigation demand. So in some areas, we expect a strong overexploitation of the aquifers where groundwater is pumped for irrigation. Whereas in other areas, we expect an increase of groundwater level if the irrigation is from surface water. Like, for example, in Emilia-Romagna plain, we have during summer very high water table level due to the irrigation infiltration from the Po River. So we expect a strong change of hydrologic cycle in the irrigated areas. And finally, along the shoreline, along the coast, we expect a salinization due to increase of groundwater overexploitation, the increase of seawater level, and so the increase of the salinization process along the shoreline. These are the main impacts that we expect concerning the connection between climate change and groundwater. But we observe these impacts also at the local scale, not only at the global scale. Also nowadays, also today, we observe these impacts. You see here 4 maps of Emilia-Romagna region in 4 different seasons of the year: fall, winter, spring, and summer. And we compare the average seasonal effective rainfall with what is effective rainfall. Effective rainfall is total precipitation minus evapotranspiration. Precipitation is the quantity of the water that is falling down to the ground. Evapotranspiration is the total quantity of the water going back to the atmosphere. This difference is the water available for runoff above the surface or recharge, infiltration down to the aquifer. So basically, this difference is I would like to skip this bar, sorry, if I to eliminate this, because I think also for you is not good to, yes, I put on the bottom, but I would like to eliminate this bar. Okay, it's not this, okay. Yeah. I'm sorry, yeah. So, what do we observe in this seasonal distribution? We observe this fact that we make the difference between two periods. Each of them is 30 years long. Why 30 years? Because 30 years is considered a representative time span to include all the normal meteorological variability of a certain location. So we have compared in this difference the 30-year time span more recent from 1991 to 2018 and the more older from 1961 to 1990. And if the difference is positive, you have color in the range between blue and violet, whereas if the difference is negative, you have values with color between yellow, orange, and red, and very dark red. So you see on the average that the effective rainfall is going to decrease in the last 30 years respect to the preceding one, with the only exception of fall period of autumn, where particularly during the main Apenninic divide, we observe an increase of average effective rainfall in a more recent times. So the distribution of the rainfall is changing, and there are more concentrated important rainfall events in fall and much lower distribution of rainfall during the other season. Particularly critical is the spring, because the spring is very important for the recharge of the aquifer. I'm sorry, okay. These are other two maps. In this case, we have put all the seasons together, and so you observe the difference between, in terms of total precipitation, P, in the left map, and of total effective rainfall, precipitation minus evapotranspiration, for all the region between the more recent and more older 30-year period. You see that basically on the average, the total effective rainfall is going to be decreasing in the last 30 years respect to the preceding one as the total amount. Whereas in terms of distribution, there is an increase during autumn season. take into your mind this difference. Another very important aspect, snow. You see, you observe that the snowpack depth, the thickness of the snow at the ground is going to be decreased from the beginning of the 21st century to nowadays. This is based upon 4 main nivometer, so the gauges measuring the depth, the thickness of the snow along the main Apenninic divide. Not only, it is going also to decrease the time by which the snow is at the ground, so the permanence of the snow to the ground. Also, this value is going to decrease in time. This is very critical for recharge to groundwater, because less snow in terms of thickness and in terms of permanence to the ground implies less recharge. And so this is a problem. This is an impact by climate change. I would like to make you reflect upon this case spring that is located in not far from Bologna. Not far from Bologna, in this position with the red small square, is the Nadia Spring. Nadia Spring is a spring in Apennines, in the municipality of Montese. It is in province of Modena, is not very far, both from Bologna and from Modena, more or less. It is located in the middle between the Panaro watershed to the left and the Reno watershed to the right. This spring, it is perhaps the most important spring of the Bologna and Modena Apennine. And as nowadays, the discharge arriving at a peak of about 70 liters per second. It's very important for the aqueduct in the Modena Panaro area. And it is uptaken by Gruppo Era Aqueduct, that it is the aqueduct, the water manager in the area. This spring was uptaken 1 century ago, in 1920, by a public work managed locally by this study, that it was written by an engineer Vecchi, 1 century ago. And this study was written in order to uptake the spring by a long drainage tunnel excavated inside the rock mass. And you see here in this picture all the water going down in the tunnel and exploited for the aqueduct. This engineer Vecchi, made a monitoring of the spring for 5 years, from 1915 to 1919. So basically 100 years ago, 1 century ago. So we can compare the discharge of the spring 1 century ago with the discharge of the spring nowadays. And this is the comparison. You see on the horizontal axis the months of the year from December to October, so from the average period of the minimum value of the spring. And on the y-axis, on the vertical axis, you see the discharge in liters per second. With the blue color, you have the nowadays behavior of the spring, 2020-2021. You see that the spring has a lower value of discharge of about 40 liters per second. It increases during the spring. It arrives to a peak in April, about 60, and then goes down to October. Well, 1 century ago, the same spring had the same pattern of discharge, but with much higher value of the discharge itself, from a bit more than 80 to a bit more than 100 liters per second. The same spring in the same location with the same land use, because the watershed of the spring basically is forested for the most in some part by agricultural activity, but not so different from nowadays, has a completely different discharge, much more value of the discharge. Why? We have considered the annual precipitation of the Montese rain gauge from 1930 to nowadays. And you see here the bar diagram of this total precipitation in millimeter from these rain gauges. Obviously, this precipitation has a variable pattern during the year, but if you observe from the far this bar diagram, you observe in some years the relative dry period where the precipitation is lower. And this dry period seems to be more regularly occurring and regularly frequent in the last years, in the last decades. Here in this bar diagram, we compare for each month of the year, we compare the average precipitation in Montese from January to December for different time period of 30 years each. So from 1930 to 1960, from the 1960 to 1990, from the 1990 to 2020. And you see that this is in the red line is the average, is the mean behavior. You see that particularly in spring, you see February, but particularly March and April, and also May, that are the 3 months more critical for recharge and for snowfall and snow melting. The precipitation is lower respect to the other 30-year period. The more recent precipitation are slower. Whereas in the autumn, more or less the value is the same. We go ahead. Sorry, because there is a slowing of the advancement of the slide. Here you see the analysis of the dry periods. And this year are the more dry periods when we had very relatively small amount of rainfall during the period from November to May. And on the y-axis, there is the interval in years between two different dry periods. And in the horizontal axis, you have the year from 1930 to nowadays. You see that going to the 1930 toward nowadays, the interval between two dry periods become shorter. And regularly in the last years, it is about 5 years period. Before it was longer. And we can see also this behavior simply by observing, I'm sorry, because simply by observing the distance between this relatively dry period, you observe that this distance is going to decrease. And so the frequency of dry period is going to increase going toward the recent period. Not only, if we put in the same Montese situation, the precipitation and the precipitation fallen from November to May, during the dry years, we observe a decrease of this precipitation. And so not only the dry events are more frequent, but during a single dry event, the total amount of precipitation is getting lower during time. So basically, in Northern Apennines, we observe, and it is already an evidence, a proof of climate change, we observe a lowering of the precipitation in the more dry periods and an increase of frequency of the dry periods. And this obviously is a stress against the groundwater flow system. What about the other aspect? Dry periods are obviously critical toward groundwater, but intense meteoric events are critical in terms of landslides that are the other. You have a coin with two faces of the coins, the coin of the dry periods and the coin and the face of the intense meteoric events. There are two faces of the same coin, that is the climate change. And you see here that if you have intense meteoric events, you observe that due to the increase of rainfall concentrated in a very short period of time, that can also determine a rising of the water table, you can have an increase of the landslide risk. So basically, climate change can transfer the impacts from 2 points of view. If you have an intense meteoric events, there is an increase of risk of landslide. If you have an increase of dry period frequency, you have an impact against groundwater systems. Two aspects of climate change on hydrologic cycle. But consider also another important issue, that we must not consider only climate change, but we have also to consider global change. Global change is a more global process that basically it is related to rapid changes of the development of the human lives in the planet as a consequence of the increase of global population, the increase of population mobility, not only economic mobility, but also migrations due to climate change, due to the war, due to the conflicts, to the increase of the quality of living, and so that the increase of the needs of the population. All these aspects have arisen around in the middle of the 20th century, and they are considered together as the big acceleration of a global process. And this global change induces an unsustainable exploitation of resources. And among resources, we have water resources. And so we have what we call overexploitation, or also called as overdrafting. Overdrafting is a synonymous of overexploitation. You are exploiting a resource at a higher rate of the rate by which the resource is renewed, is reconstituted in the case of water, by the precipitation. If you exploit the resource at a higher rate, you have an unsustainable exploitation of the resource. it's very coherent. The strong increase of the global population that we are registering from the mid of the 20th century and the strong increase of the emission of CO2 in the atmosphere that is occurring from the mid of the 20th century. Two processes with a very high rate, two processes very different from the preceding rates, and they are coherently going up in the last part of the 20th century and obviously at the beginning of this century. And all this process induce some strong modification of different aspects. With these aspects, we can call them as global change actions. Basically, all these are related to the modification of land use. For example, clearing natural vegetation and forest. For example, converting pasture to arable land. For example, the intensifying of irrigation agriculture with the importing of surface water. The reforestation and afforestation with commercial woodland. All these processes have an impact against water resources. And obviously, not last, urbanization and migrations. And this has important consequences in groundwater, in terms of pollution, in terms of affecting recharge, affecting salinity, and affecting storage. So the quantity of groundwater stored in the aquifer. And the effects of global change are, could be much more intense than the effects of climate change. And often these two processes go ahead in parallel because the climate change affects the global change processes. Irrigation, for example, take into account that at the global scale, irrigation accounts for about 70% of total global freshwater withdrawal. So the most part of the water, both surface water and groundwater, is withdrawn, is exploited for irrigation. It's very important, the contribution of irrigation. And irrigation, the irrigation practices has very important effects, could have very important effects against I'm not able to skip this bar, but by the way, I try to move it when in order not to cover the slide. Yes, effects of irrigation practices. So you have the groundwater depletion. In the case you are utilizing groundwater for irrigation, or on the other hand, you can have groundwater accumulation as a result of used surface water as irrigation water. You can have a change of evapotranspiration that in some case could be an increase of evapotranspiration due to irrigation, and a degradation of groundwater quality because irrigation is accompanied by the use of pesticides and other chemicals that can worsen the quality of groundwater. So irrigation has a strong impact on water resources. But I could give you some other ideas about the water that we consume in our standard way of living. Take into account that a gatherer, hunter, human being, in Italian we say cacciatore raccoglitore, a human being that lives in a pre-technological and also pre-agricultural way, uses for each life about 2-3 liters of water per day for its domestic and drinkable uses. Very small quantity. Basically, you need a couple of liters, 2 or 3 liters of water per day at least, to guarantee your drinking needs, your cooking needs, your cleaning and domestic needs. But in a toilet, double VC single flow pulse, you waste 15 liters of water. So about 5 times the needs of one single human being. And in Bologna, for example, Gruppo Era, the aqueduct of Bologna, must provide to every citizen at least 250 liters per day for the needs of the citizens due to the domestic shower, washing machine, cooking activities, all the water uses for which you pay the bill to Gruppo Era in Bologna. 250 per day, per person. So we have started from 3 liters from a gatherer, hunter, human being. And in Europe, we are more or less around 250. And what about the North Americans that generally are more exploiting water resources? Take into account that an average citizen in New York have a supply of about 500 liters per day. So we have started from 3, and in some places of the planet, we are arriving to 500, with an increase of 2 orders of magnitude between the basic needs of a gatherer, hunter, human being, and a modern citizen in the North America situation. If you accompany this with the increase of the world population, of the change of the standard way of living of global population, take into account, for example, Chinese that have changed their society from a basically agricultural society to a very urban and industrial society, you can evaluate the increase of pressure on water resources. Why it is wise to use groundwater as main groundwater resource? Because groundwater is already naturally filtered by the porous medium. We have seen in the preceding lesson that groundwater flows inside the porous medium, so it is filtered by this flow. It's more protected from pollution if we don't pollute it. It could occur also in arid areas, and in some places it could be exploited with higher quantity respect to surface water. Basically, it's better to exploit groundwater respect to surface water as main destination of freshwater use. There are obviously some drawbacks about the use of groundwater. Not everywhere is occurring groundwater. Sometimes groundwater is strongly mineralized, so it's full of salt and could also be naturally not drinkable. It's more difficult to remediate a contaminated aquifer respect to remediate from pollution a contaminated surface water system. And we have in some places strong effects of overdrafting, salinization, subsidence, diminishing of environmental flows. So also if we know that the use of groundwater has some advantages, we also see that groundwater in some places is subjected to a strong overexploitation. Consider these data that compare the global use and the Emilia-Romagna use. We are not so different between the two. This bucket is the global scale withdrawals of fresh water for all purposes. So irrigation, drinkable use, and industrial use. At the global scale, at the planet scale, this is a budget of 2018. So it's a recent global budget. About 2/3 of global scale water is derived from surface water. So from rivers, from streams, from reservoirs, whereas 1/3 is exploited by groundwater. Also in Emilia-Romagna, the proportion is more or less the same. And you see the comparison according to the ARPAE water budget is a bit older than the other one, but it's more or less acceptable for our estimation. 2/3, about 70% for surface water, 31% from groundwater. So also if you recall, groundwater is much more huge in terms of volume at the global scale. The majority of exploitation is from surface water. Why? Because it is more easy, it is more convenient to exploit surface water. It's more near to the ground, it's more available, it's more easy to take out surface water from a reservoir or a big river. Whereas groundwater must be pumped and it is more technically difficult to exploit groundwater. Let's consider the situation in Italy, for example, of the use of groundwater and surface water among different regions. You see the different regions in Italy, and for each region you have a pie diagram, and the color of the slices of the pie is depending on the main source of water for public water supply, so for aqueduct. If you have the black color, the source is represented by springs. Otherwise, you have surface water with the light gray and the wells as the dark gray. You see that in Italy, there is a very evident difference between the northern Italy and Tuscany respect to the central Italy and southern one. In central and southern Italy prevail springs as main source of public water supply. You see in Latium, in Abruzzi, in Marche, in Campania, in Sicily, in Calabria, in Puglia, you see that the majority of public water supply derive from spring. Why? Because along the Apennines, you have many aquifers, most of them karstic and volcanic in nature, that are capable to sustain big discharge springs and so provide good quantity water to these aqueducts. On the other hand, in northern Italy, you have a very big plain, Padana Plain. In the Apennines, we don't have much permeable materials, much permeable rocks. And for that reason, wells are prevailing as source of groundwater. In some regions, for example, Sardinia, you see that surface water is prevailing because Sardinia has no big plains, has no permeable rocks, and so the big reservoirs, the big surface reservoirs are the main source of public water supply. So you see that public water supply in Italy is related to the geology, basically, of the region. And for Emilia-Romagna, here we have the differentiation between different types of use: agriculture, public water supply, and industry. And you see that the big quantity of the water, of the fresh water resources in Emilia-Romagna are used for agriculture purposes, very big proportion, and the surface water in white is much more dominant respect to the groundwater. Whereas for public water supply, you have an increase of the proportion for groundwater respect to the surface water. And for industrial use, we are all more or less in the same proportion. So you see that the bucket of agriculture is much bigger than the bucket for public water supply, than the bucket for industry. The major quantity of fresh water in Emilia-Romagna are exploited for irrigation, for agriculture. And inside the consumption for public water supply, groundwater, either from wells or springs, is dominant respect to surface water. And this is important because groundwater is naturally filtered and so has a better quality respect to surface water. Groundwater at a global scale is subjected to a very strong exploitation. And this exploitation is much more intense in several parts of the world, and the groundwater withdrawals are still increasing. Generally, at a global scale, 36% of potable water supply is derived from groundwater, 42% is derived for irrigation, and 24% is derived for industry of the total groundwater global use. And these are a list of countries where withdrawal intensity is highest due to a strong pressure from the population over the water resources. And you see that many of these countries are overpopulated or are located in arid and subarid climates. Which are the undesired effects of overdrafting? Overdrafting is the process by which you are exploiting the groundwater at an unsustainable rate. So a rate that is not sustained by the hydrologic cycle, by the hydrologic natural process. So basically, you are exploited the resource beyond what we can term as safe or sustainable yield. And these effects could be grouped in 4 types, and we will see some examples of these 4 types of effects: the watering, salinization, subsidence, and drying up of springs and streams due to tunneling. This is a particular aspect of overexploitation that, with the development of big transportation system, could become very important. Let's consider these examples. The watering. It's easy to describe the watering. Imagine that you are located in a region, you have a groundwater below the ground. This dashed line identifies the water table. You have shallow wells exploiting the groundwater, but at a certain point, you drill a more deep well because you need more quantity of groundwater for irrigation, for example, for intensive irrigation. And with this strong pumping, you draw down the water level, you see the formation of what we call a cone of depression, a cone of piezometric depression inside the aquifer. And this depression dry up, desiccate the shallow wells because the water table is going to be draw lower, in a lower level respect to the bottom of these wells. So one intense pumping in one place eliminates the water from shallow wells. This is a typical example of the watering of the aquifer. And the watering of the aquifer, these effects of water scarcity is more and more impacting, particularly very intensively concentrated conurbation of people in many countries in the world, with an intense request of water for different uses. Not only the watering, but all other very important consequences are related to the overexploitation of the aquifer. One of them is subsidence. You know that the subsidence is a geological process, is a natural process by which the ground is going to be subjected to a process of lowering of elevation. This is very normal in alluvial basins. Generally, like for example in Emilia-Romagna plain, you have a regional normal rate of natural subsidence that is around 0.72 millimeters per year. It's a very low rate. And we don't feel it. We don't have the experience of them, of this low rate, because the natural process of sedimentation by the rivers replaces these subsidence. And so basically the ground level stay in an equilibrium condition. You have a very light decrease of the position of the ground, but you have the supply of sediments from the river. And so the level, the general level of the ground almost stays in an equilibrium condition. But if you have strong pumping by wells, you can induce an artificial subsidence rate that it is much higher than the natural one, with rates that are between 30 and 70 millimeters per year, so about one order of magnitude higher respect to the natural rate. Why you have this? Because when you pump out the groundwater from the aquifer, you have a depressurization of the water in the aquifer. The water is subjected to a lowering of the pressure. And if the water inside the ground is subjected to a lowering of the pressure, the water itself is less capable to sustain the load of the sediments above it. And so basically it's the same when you open the valve of a tire of a wheel, you have the air escaping out of the valve, and the thickness of the tire is going to be depressed. It's the same way in the artificial subsidence. You pump out groundwater, you depress the groundwater, and the thickness particularly of clayey and silty layer, are going to be reduced by this pumping activity. And this is reflected on the ground by ground movements. And so buildings could have some cracks and instability problems. And also canals can invert their slope. And you can have also damages and instability problems against the monuments, against the dams, levees, and also the problem of salt encroachment, salt intrusion along the coastal areas. In this picture, you see a very extreme example of artificial subsidence. Here we are in California, in one internal basin, San Joaquin Valley, where they had a very strong development of irrigation for the orchards and agricultural crops produced there. All the water for the irrigation was pumped from groundwater because there were no surface water available. It is a subarid climate, very arid in some places. And you see that in 1925, the ground elevation was there. In 1955, it decreased in such a way. And in 1977, it decreased at the position of this man. And the man is making the scale for this very big lowering of the ground. Then the water use of the location changed, moved to other sources, for example, reservoirs from other watersheds. But you can see how much could be the decrease of ground surface due to pumping. Here you see a map in Emilia-Romagna plain, in Padana plain, where you see the distribution of subsidence rate in millimeters per year in the second half of the 20th century. You see that you have an hot spot in Bologna area and a hot spot in the delta of the Po River, both and a secondary spot near Ravenna. These two spots are related to groundwater pumping. In Bologna, for the pumping of the wells of the aqueduct, and also for industrial wells in the area, with subsidence rate high up to 66 centimeters per year, 60 millimeters per year, and also in the delta of the Po River for the pumping of the waters, groundwater associated to the methane reservoir in the area of the Po River delta. Now this methane abstraction has ceased, was interrupted, also because there was a very big problem of subsidence with the risk of flooding of all this area, that it is very near to the average sea level, and in some places also below the average sea level. You see here a profile of the subsidence rate along Via Emilia, from Piacenza to the northwest to Rimini to the southeast, and it is in millimeter per year, this subsidence rate. And you see the maximum rate is concentrated in the Bologna area, where you have the higher groundwater pumping scheme due to the aqueduct near Bologna. Another consequence of overexploitation is the salinization of the aquifer. And in this picture, in this drawing, you see different ways how groundwater could be salinized due to overexploitation. The most common situation is encountered along the shoreline. Along the shoreline, in natural conditions, you have a contact between two fluids with different density. Fresh water, lighter, and salt water, denser. As a distribution of density, the light water is going to float over the salt water with the formation of an interface dividing the two waters that are not mixing between each other. But if in the coastal areas, you have a strong pumping of groundwater, you have a piezometric depression and an effect of intrusion of salt water from the sea to the continent. Higher is the intensity of groundwater depletion, higher is the salt water intrusion. And so you have a salinization of the aquifer. Let's concentrate now here in the middle of this picture, of this drawing. You see that the salt water is very deep into the ground. This is a particular situation typical of alluvial basin, like for example, Po Plain, Emilia-Romagna Plain, where you have very deep into the ground, below the ground, also a depth of about 1,000 meters, 2,000 meters, you have very saline water, very salty water for natural process, because they were deposited in the past when the Emilia-Romagna Plain was a marine gulf, and so the water trapped in the sediments was marine water, was very salty, and also because when the water stays for a long time inside the sediments, the water is going to become very salty. But if you intensively pump groundwater, fresh groundwater in the shallow aquifers, you can also abstract saline water in the deeper part, and more intense is your pumping, more quantity of salty groundwater you can abstract from below the ground. So also in this case, salinization is a proxy of an aquifer subjected to overexploitation. These are the two main examples, the two main processes of groundwater salinization along the coast and due to intensive pumping in alluvial basins. There are many other aspects of salinization of the groundwater resources due, for example, to increased evapotranspiration in agricultural areas, to the pumping of oil reservoirs with the discharge of very salinized groundwater formations and so on. But basically, these are the two more important. Here in this picture, you can see very well the situation of the effect of intense pumping due to the need of water in these coastal areas. And you see here, you see on the left the seawater, the salty groundwater below the seawater, the fresh groundwater below the continent. This is the interface dividing the salty water on the left and the fresh water on the right. And the pumping determine a raise of the interface and the salinization of the pumped groundwater. So you have a salinization of the system. Fourth example of the effects of overexploitation is the effects due to the excavations of transportation systems. Transportation systems are basically tunnels, and tunnels are more and more drilled to transport people. not only people, but also, for example, to transport water in water derivation scheme by the hydroelectric power, and to transport water from one watershed to other watershed, you use tunnels transporting water, or railways, or highways. In all these examples, the tunnels are excavations drilled through the mountains, and tunnels drain the groundwater, normally drain the groundwater. Also for exploit groundwater. We have seen at the beginning of this lesson, the Nadia spring in Emilia Apennines that was uptaken by drilling a tunnel. So it is also a way to abstract groundwater. You see a tunnel in profile and the lowering of water table respect to the natural position. And so you have a free drainage tunnels that are collecting groundwater. If you completely seal the tunnels, you avoid this process. But in this way, the tunneling is much more costly because the sealing of the tunnels, it's a very expensive approach. Like, for example, the tunnel below the channel between the UK and France. It was completely sealed, obviously, because it is below the sea floor. I would like to talk to you about an example of the impact of big tunneling against groundwater resources. This is another good example of global change, because this type of big transportation systems are more and more developed along in many countries. And from one point of view, this is a safe way to transport goods and people, because you have lower impact on the surface, you have lower problems of pollution by the emissions of gases by the traffics, and it's more safe to transport goods and people below the ground, but has an impact against groundwater resources. Here you see the example of the Gran Sasso Tunnel. Gran Sasso Tunnel was a tunnel for highway connecting Rome and Teramo, so through the Central Apennines. And these two tunnels were drilled about during the 70s, so about 50 years ago, to connect two sides of the Gran Sasso Massif. Gran Sasso Massif is a karstic system, so has a very high permeability. There is a groundwater flow very active inside the Gran Sasso. And so the effects of these two tunnels was to drain groundwater, to collect groundwater. And now groundwater is collected by these two tunnels and is transported by gravity to the portals of the tunnel. And it is also used for public water supply, both in the Teramo side of the tunnel towards the Adriatic Sea, or in the Aquila side of the tunnel towards the western flank of the Gran Sasso Massif. The steady state drainage of these two tunnels is much high, 1.5 cubic meters per second of groundwater that it is continuously drained by the two tunnels towards the Teraman and the Aquilan side. Another example is much nearer to us. It is in the Northern Apennines between Florence and Bologna. You know that in this part of Northern Apennines has been drilled a tunnel for the high-speed train connection between Florence and Bologna. And this connection is based upon a series of tunnels excavated below the ground. You see these on the left are typical examples of rocks that are outcropping in these Northern Apennines. This is a geological map of Northern Apennines. And you see particularly these yellow color outcrops of rocks is of this type of rock that are called turbidites, torbiditi in Italian. They are rocks deposited in very deep marine environment due to a sedimentation of big landslides with arenites, sandstone basically, and fine grained materials. They are not so permeable like Gran Sasso limestones. So the designer of these tunnels in Northern Apennines expected much lower quantity of water drained from the tunnels. But by the way, these excavations has induced very strong impact against groundwater resources. Here you see in the slide the line of the connection of the high-speed train connection between Florence and Bologna. This is a typical aspect, typical sightseeing of turbiditic sediments in Tuscan Emilian Apennines. Here you see here we are more or less in the middle of the line, and you have the trains that are running along this line from Bologna to Florence and vice versa. And this video is more or less located in the Santerno River Valley, more or less in this part of the line. And below, in the slide below, you see two big quantity of water draining out from two portals of the tunnel. Nowadays, these two discharges are about 100 liters per second from one side and from the other side of one of these main tunnels. Here we are in the Mugello Basin, and here we are in the Santerno River watershed. And these two quantities of water have been drained by the tunnel. Sorry, because there is a slowing. Yes, this is an image of the tunnel completed. Nowadays, we have two tracks along the tunnel. The tunnel is completely lined by concrete, obviously, but there is a system of drainage of the water because the tunnels are not designed to sustain a very high groundwater heat above them. And so they have to drain the water and to collect the water at the base. You see here a sketch of the draining system of the tunnels. The groundwater is flowing along the vault of the tunnel, and then it is drained by this system and connected to two central draining pipes, and the central draining pipes by gravity convey the water to the outlet of the tunnel. And so finally, the water is arriving to the surface water system here in these two places that I have shown to you before. And it's interesting to say the evolution of the total discharge drained by the different tunnels, particularly in Tuscany sector of the line during the excavations of the tunnel and nowadays. You see here the drainage behavior from 1999, from 1998 to 2009. From 2009, the trains begin to run along the line with the passengers. And it's better to observe this graph in a logarithmic scale. You see that the main, like for example, this blue line, you see a very regular cyclic behavior of discharge, because basically these tunnels have become like a big spring. They continuously drain groundwater with the seasonal type behavior, with the peak in spring and the low discharge at the end of the summer. And this is very regular. And what's the message from this hydrograph? That we have created, they have created a connection between the surface water and the tunnel water. And so the tunnel water basically is behaving like a big spring, producing this regular behavior of the water. But basically this water is subtracted from the surface. And so there is an impact against the surface. Here you see the line from Florence to the Raticosa Pass, so more or less in the Tuscan sector of the line. And all these orange areas that you see are continuous in some places have been subjected to a strong impact of groundwater resources, and many springs were desiccated completely or seasonally. These are all the springs that were desiccated, and they are based upon the distance from the line and the elevation from the tunnels. And also some streams now have their environmental flows during summer completely destroyed by this drainage. You see here an example. This is a photo taken up in January 2018. We are in the confluence of two streams in this area, the Rovigo stream from here and the Vecchione stream from here. But in another season, and the other season is summer, July 2018, you see that this Rovigo stream has obviously a lower quantity of water because we are in summer, but the Vecchione stream on the right is completely dry. And this dry up, this desiccation of the stream is due to the groundwater draining of the tunnel. Before the tunneling, this stream never desiccated, also during summer. And so obviously this is an impact of big transportation system of groundwater flow. And this is a very evident example of this impact. The last slides of this first part of the lesson are devoted to another example of a process that we can consider as an example of impact of global change. The big landslide of Vajont. I think that perhaps many of you know this big event that happened in Longarone municipality in 1963. So it's about 60 years ago, when a big mass of rock produced a very enormous landslide, falling down in the basin of the Vajont stream, producing a very big tsunami, a very big wave that completely destroyed Longarone village, and with casualties that were higher than 2,000 people. This was a landslide, so it was a natural phenomenon, but it was induced by men. It was induced by, in particular, the use of the water for hydroelectric power generation. I have put to you this link, that is the link to the orazione, to the speech of Marco Paolini, that it was held in Longarone location in 1997. It is an incredible monologue of Marco Paolini that I recommend very much to all of you to listen to this presentation of the event of Vajont landslide. A bit more detail about this event that I think it's very representative of what we consider a not predictable event. This is a site of the Vajont Valley, and with a sightseeing from the east. Basically, what's happened in this place? They built a dam, the Vajont Dam, closing the very narrow gorge of Vajont stream and producing, obviously, like all dam, a lake up gradient of the dam. This is the lake, the remnant of the lake, because this image is after the fall of the landslide. Here you see the scar of the landslide falling down along the slope of the Mount Tok that is here, and all this block of rock falling down, filling the lake. But this very big amount of rock falling down with a very incredible speed, about 100 kilometers per hour. So you have to imagine a very big mass of a piece of a mountain arriving down immediately and suddenly with a velocity of about 100 kilometers per hour, arriving with a splash, with an enormous splash down into the lake. This splash produced a big tsunami that arose from the lake and jumped over the dam and arrived to the Longarone village below the dam, completely flooding the village and destroying all the buildings, all the people, all the activities there. Why do we have a so strong phenomenon? Because we can observe this graph. I think it's useful to understand. The engineers that design the dam and the reservoir, after the construction of the dam, began to fill the reservoir, and so to increase the level of the water. You see here on the y-axis the level of the water in the reservoir in meters above sea level, and you see here the process of the filling up of the reservoir. Note that during the filling up of the reservoir, you had some movement of the rock mass. The rock landslide was active, was going ahead, but in a very slow rate, a normal rate, for so big landslides, because generally that big landslides have a very slow movement. So the engineers believed that they can control the very slow movement of the landslide, accompanying it through their slow movement towards the lake. And they continue to increase the level of the reservoir. Then they make some process of emptying the reservoir, because during the initial phase, you have to register the emptying and filling again of the reservoir. But at a certain time, when they arrived to 710 meters of elevation of the water level above the average sea level, immediately the landslide started in a very impressive and sudden way, with a total movement of all the slope of the mountain going down to the lake. And this speed, about 100 kilometers per hour, was absolutely not predictable in terms of the knowledge of the processes of landslides, but it was induced by man's activity. So it's an example of global change action, of big activity, of big public works that could have an effect against the water resources in terms of effects for landsliding. This process obviously had a strong impact on the knowledge of landslide, and for that reason, from then to nowadays, it became much more difficult to build up dams in watersheds where you have some landsliding process going on. Well, I think that we can have a break, because for 2:45, we are 1.5 hours. If you have some questions, otherwise we stay a bit relaxing, waiting for the second part of the lesson here. Okay. Julia, are you listening to my voice? It's okay? Okay, Serena, okay. Well, so we are in the last of my lessons of this, my talk. Something, we have seen the process of landslides, the process of groundwater flow. We have seen the impacts of climate change in relationship to landslides and in relationship to groundwater flow. And we have seen that these impacts are due basically to two main origins: the increase of extreme events in terms of intense meteoric events and in terms of droughts from the side of climate change, and the overexploitation of the aquifers and the overexploitation, not sustainable exploitation of water resources due to global change. Then what can we do against these imbalance, unsteady conditions, towards these instability conditions of overexploitation of the resources? And so the matter is the issues of assessment, of mitigation, and of adaptation. And I will give you some clues, some concepts again relationship to these aspects. So let's start with the problem of the assessment. The assessment, we could say also the forecast, la previsione of the landslides and the increase of the risk of landslides due to the increase of meteoric events. This basically is an issue of probability. And one main pathways to have the chance to assess the probability of landslide occurrence is to have a good monitoring, a good recording, a good observation network of landslides processes in order to forecast the future development. I will give you an example, very simple, in order to give you the idea of the importance of monitoring. Consider this phenomenon is rockfall of debris and rocks along a highway. We are in the western part of Canada in British Columbia, along a highway called Highway 99 between Vancouver and Squamish. Here the hazard is rockfall by gravity, and the rockfall is obviously enhanced by intensive meteoric event. So basically the question is, what is the probability of the outcome of an event with certain intensity? How much probable is a landslide in a certain part of a street? And so how much high is the risk to have undesired effects due to this landslide process? It's a probability analysis problem. So observe this graph. This graph put in relationship the volume in cubic meter of the mass of the rock that it is landsliding down to the street. And in the vertical axis, both axes are in logarithmic scale. In the vertical axis, you have the cumulative frequency per year of these events. So 1 is 1 event per year. 10 is 10 events per year along the street. 100 is 100 events per year, and so on. It's easy to understand the relationship between higher is the volume of the possible rock slide falling to the street, higher is the cubic meter volume, and lower is the probability. Where lower is the volume and higher is the frequency during the year. So for example, you see on the right, there is an example. If you want to know the probability outcome of the intensity of the rock fall in the interval between 1 and 10 cubic meter, so 1 is here on the x-axis and 10 is here on the x-axis, you go to derive the probability of these two examples. It is between 7 and 2. So we have a 5 times per year frequency of event between 1 and 10 cubic meters of rock. How were we able to reconstruct this probability plot between the volume of the fall of the rock falling and the cumulative frequency? Is based upon observations. We have a very long time series of observations, and from these observations we have derived the risk. It's the same for many of hydrogeological risk or geological risk. The time series in the past give you an idea of the probability outcome of the event. And higher is the intensity of the event, lower is the probability respect to time. But obviously, probability is not the only way to make to have a relationship with the problem of the risk, because another is the mapping of the part of the slope that are more exposed to rock instability, and to avoid to have streets or other public buildings and public works below the areas more exposed to landsliding. This short example gives you the idea that the evaluation of the probability of an extreme event is basically based upon a probability analysis. So a frequency expected that it is inversely proportional to the intensity of the event. What about mitigation of geological hazards? Reflect upon this slide. Here, there is a list of factors that increase the destabilization forces along a slope. We have seen that we have a landslide when the factors destabilizing the slope are more intense respect to the factors that stabilize the slope. When this ratio is unbalanced towards the increasing of destabilization, you have a landslide. And in this list, you have many factors that could be related also to climate change, the blue one, and man-made, and so to the global change, the red one. For example, you can have a landslide if you have the removal of lateral sustainment of a slope, something that is able to hold stable a slope. For example, melting of mountain glaciers. In mountain areas, the melting of glaciers and so the vanishing of the ice mass has an effect of removal the lateral sustainment of rock slope with the formation of destructive landslides. So this removal is a consequence of global warming. Global warming with the melting of mountain glaciers could determine the inducing of landslides, but also man's activity, excavations, quarries, digging on canals, removal of retaining measures are all factors of possible landsliding. Also erosion, obviously. Erosion, it's a natural phenomenon. But these two are in some way connected to climate change or man-made activities. But what about overload? When you have intense rainfall and so intense meteoric event, you can have increase of soil density due to saturation of the water, and you can have an increase of landslide risk. But this overload could also be due to man's activity. For example, the building up of embankments, infrastructure like mine tailings, landfills, or also leakage from water pipes and sewers. All these processes are man-made And all this process could determine an increase of risk of landsliding. Also, the artificial increase of the slope by excavation and fillings, or lateral additional stress due to water filtration along the slope, or transient stress like vibrations by explosions, vehicles, trains, machineries, etc. All examples are man-made or climate change induced factors that can determine an increase of the probability of landslide that has been related to the observation of a natural evolution of a slope. So these values are derived from observations, but the observations is based upon the past experience. But these values are a complication of the observation because you can have the increase of the factors of landsliding due to these man-made or climate change induced factors. Let's go to the aquifers. Let's go to groundwater flow. One good way to mitigate the effects of climate and global change is to base our groundwater exploitation upon aquifers, because we have already seen that aquifers are very resilient to climate change. In many situations, aquifers have a huge volume of stored groundwater, so they have a very big stock of water below the ground. If the aquifers are permeable, they could have a good aptitude to water abstraction. If the aquifers are rather deep into the ground, they are well protected against pollution, and so they behave as low vulnerable to pollution. And if they have a good groundwater quality and high recharge and renewal rate, they are ideal for the management and exploitation of groundwater. But we have seen that aquifers, also if have ideal conditions, can be overexploited by man. So what can we do in order to mitigate the effects of groundwater overexploitation? A very good approach, a very smart solution to manage effects of climate change is the so-called integrated management of surface water and groundwater. This is revolutionary from different point of views, because you see that surface water, and so the streams, lakes, reservoirs, and the groundwater, so the water below the ground, are not seen as two separate bodies, are not seen as separate realms, but are strongly interconnected between each other. And taking into account this strong interconnection, we can manage them in an integrated way. The integrated exploitation of groundwater and water resources, it's a very old approach. Consider this slide. In the past of thousands of years ago, a procedure very used from many, from some people, from some culture in some parts of the world, was the so-called rain harvesting. Rain harvesting literally means la coltivazione della pioggia. So considering rain as a crop, not coming from the ground, but coming from the sky, and trying to collect rainfall in order to sustain the droughts period, the dry period. This rain harvesting procedure was, for example, adopted in the desert of Negev in Israel, in nowadays Israel, 2,000 years ago, from an ancient population called the Nabatei. They dig canals along ground contours, so more or less in a subhorizontal situations, in order to collect what? To collect overland flow, so to collect the excess of the water originating at the surface during the more rainy periods, and convey this surface water in excess to an underground tank located, in this case, on the right of the slide. So reflect. Climate change, this is an example of the past in order to give you the philosophy of this approach. If climate change is based upon an increase of extreme events, where you have high intensity rainfall events interspersed with the low period of dry condition, low period of droughts, we can imagine to re-equilibrate this imbalance, and so to in some way store the excess of water that you can have during the more intense rainy period, and transfer this excess to the groundwater below the ground in order to relieve the suffer due to the overexploitation. This of the Nabatei, it is a prehistoric example, a very old example, but we can have still nowadays more technical sound and more useful approach. Today, we have this term in some situation that is called the rain harvesting. Rain harvesting could be adopted and could be installed by having some surface that collect rainwater, and from this surface the water is conveyed to directly the groundwater, for example, so to refilling up the aquifer when you have an excess of the water at the ground. And this can, for example, be used to recharge groundwater during the period where you have an excess water in the surface. Here you see two examples. The general approach is the same. You have a surface collecting the rainfall directly and conveying the rainfall down into deeper wells. And these deeper wells then can be location of pumping of groundwater during the dry seasons, during the dry period. It's very simple, this approach. But we can go ahead from this concept philosophy to a more technically sound and developed process that nowadays it is called artificial recharge. What is artificial recharge? Is to recharge groundwater in an artificial way, transferring to groundwater the excess of surface water coming out from the excess during the more rainy period. And so we can enhance, increase the direct recharge or lateral recharge in order to contrast the loss of groundwater storage and replenish, recharge the aquifers, and particularly in the coastal area, preventing or slowing saltwater intrusion. Basically, the philosophy is to transfer the seasonal excess of surface water down to stressed groundwater reservoirs. Imagine that during summer, you pump out a lot of groundwater from the aquifers, and particularly in arid and subarid climates, like also Mediterranean ones, you can have a strong, intensive overexploitation of the aquifers during summer. And so aquifers during summer are stressed, are in a stress condition. But we know, we have seen in the preceding lesson, that in some places, also in Emilia-Romagna, you have an increase of rainfall intensity during the autumn, because you have many intensing meteoric events, very concentrated in time and space. And they produce a lot of water, but most of this water is going to flow over the ground, not to infiltrate, because the quantity of water arriving in a very short time interval is very high. So you don't have a very much effective transfer of water from the surface to the ground, because most of the water is flowing above the ground. But with artificial recharge, you try to make something like a blood transfusion. In this sense, it is a water transfusion, and you transfer the excess of water to the surface going down to the ground. We have a definition of this technical procedure, and this definition is MAR. The definition of MAR is managed aquifer recharge, because it's a recharge of the aquifer, but is managed, is man-controlled, is designed, is managed in some way. And this MAR is the definition for the planned human activity devoted to increase the groundwater sustainable yield through enhancement tools of natural direct recharge or forced infiltration of surface water into the aquifer. So in some way, we try to enhance, to increase the capacity of the water to go from the surface down below into the ground. Is a transfusion of the water. Here you see a list of possible approaches with the transfer of the water from the surface to the ground. Consider, for example, a river. We are, generally speaking, we are not in the case of managed aquifer recharge, we are not talking about the transfer of rainfall directly to the ground. It was the approach of rain harvesting. Here, generally, we are talking of transferring surface water, so the river water, to the ground. This process is natural in many places, because we know that the river water could be connected to groundwater through the infiltration below the riverbed, and so you have the infiltration. But we can enhance this infiltration, diverting what? Diverting canals. You see here from this river some canals, and these canals could be connected to surface spreading basin or recharge trench. Surface spreading basin could be, for example, dismissed quarries, cave abbandonate, or location where you don't have a direct use of the landscape, and you can use these spreading basin that are basically some places of the ground where you have a very permeable bottom. And from this basin, you have the infiltration of the water down to the aquifer. Or you can excavate some recharge trench into the ground. And from the recharge trench, the water diverted from the river is subjected to infiltration into the subsoil. And in such a way, you recharge the aquifer during the period where you have an excess of river flow. And so you divert this excess of river flow inside the ground. Often, these diversion basins are also areas where naturally the river water is conveyed during floods. And so from a certain point of view, you reduce the risk of the flood because you let the river wandering around these areas. And from these areas, at the same time, a certain quantity of water is infiltrating down into the ground, arriving to the aquifer. So you have actually a modification of the hydrologic cycle, in some way inducing an increase of recharge. These two approaches, the surface spreading basin and the recharge trench, are good for shallow aquifers, so aquifers very near to the ground surface. But you can use another approach in order to reinject water down deep into deeper aquifers by injection wells. In this example, you use wells like boreholes, like holes, where you inject the water coming from this diversion canal and you recharge the aquifer below. The procedure has to be surveilled and monitored because obviously you must care that the water used for the injection in the groundwater must not be contaminated, must not be turbid, and so must be safe in order to provide good quality water into the ground. But it's a very smart and useful approach. Also in Emilia-Romagna now, they are having a pilot project in the Conca, in the Marecchia basin near Rimini, in the Romagna area, where they used some dismissed quarries in order to reinject into the ground the river from the water from the Marecchia River into the aquifers that are stressed by pumping. And it is a good example on how we can adapt to the climate change and mitigate the effects of climate change by transferring the excess of the water from the surface to the ground. Another example is adaptation. We have already seen, and we see in this slide, that aquifers could have groundwater flow in the ground very different in relation to time scale. We have, for example, very shallow aquifers where the water infiltrates, travels into the porous medium, and arrives to outcrop in a very few time scale, for example, in days. But we have much more deeper systems where the water is flowing along centuries, also along millennia. So basically, more deep you go into the ground and more old is the water that has infiltrated. But this water, so, could be infiltrated many thousands of years ago, where the climate was very different from the climate of the actual period. This is very important. Groundwater flow is much more retarded for the deeper aquifers respect to the nowadays climate. You have to reflect upon the fact that groundwater could be considered like a bank. Shallow aquifers are banking system where you have an income, a salary, you put the money in the bank account, but you expend all your money during 1 month. And so there is an equilibrium between the salary and the expenditure. And your bank account is always very low in quantity because all that you earn, you pay and you expend. There is an equilibrium very fast. If in a certain month you are without job, you don't have the salary and you are in crisis because there is no more money in the bank account to guarantee your life. But in the more deeper part of the ground, this is not in the same way because you can have aquifers that were recharged thousands of years ago in completely different climatic condition and now are filled with water and are useful to react to the climate change. I make you an example. You see here in this slide an oasis. So a strange thing, a mismatch, because you see an abundant hot spot of fresh water in the middle of the desert. How is possible this fact? Due to a very important geological phenomenon that is called fossil aquifer. You know what is a fossil? A fossil is a remnant, is a residue of a very old life. Like, for example, the skeleton of the Tyrannosaurus is a fossil, is a remnant of a specimen living millions of years ago. We have also fossils aquifer, are reservoirs with a huge volume of groundwater, and these reservoirs, much deep into the ground, were recharged in a completely different geologic climate conditions thousands of years ago. Examples of these fossils aquifer are located throughout the world. For example, in Northern Africa, in Southern Africa, in the Great Artesian Basin in Australia, Guarani Aquifer, High Plains Aquifer. I would like to concentrate in this Nubian sandstone aquifer system. This is a very huge groundwater reservoir located at the boundaries between Egypt, Libya, Chad, and Sudan in Northern Africa. And consider the numbers. The storage is incredible. The storage of the water is 150 cubic kilometers, 150 thousands of cubic cubic kilometers of water. And the nowadays recharge is very low, is 5 millimeters per year. Why? Because these aquifers is located in a completed arid climate, the Sahara Desert, nowadays. But why we have a so strong, huge quantity of water? Because this groundwater was recharged about 10,000 of years ago when the Sahara was a pluvial climate, very different from the climate nowadays. And so this is an extreme example of the strong resilience of groundwater flow respect to climate change. The climate has completely changed between 10,000 of years ago to nowadays. Nowadays, we are in arid condition, and nowadays we have a plenty of groundwater below the ground that is used, obviously, from Libyan and Egyptian people for their uses. Obviously, it is a mining exploitation of groundwater because the actual recharge is no more able to sustain the pumping. But it's a good example of how groundwater could represent a good way to react to climate change, because you can have a buffer in some way to respond to the stress posed by the dry period in the surface. It is if you can also see in this a small provocation, because it is an extreme condition, but it's a good example of how groundwater could represent a good way to react to climate change stress in the surface. As a last slide, I have finished now. You can see here a link useful for you. This is the site of the IAH, the International Association of Hydrogeologists. You can find there a very interesting information also on the basis of videos and communication materials about groundwater management and management of water resources at the global scale, also in relationship to the effects of climate change. I have finished. If you have questions, if you need some support from myself, you can write to me. My mail is alessandro.gargini, name.surname@unibo.it. And it was a pleasure to have these lessons for me, and have a good prosecution with the course of Alberto. I have finished. Thank you for the translation, and have a good day to everybody. Alberto is arriving.
Yeah, we can close the registration. Grazie Giulia e Serena. Noi ci sentiamo.